What's up, algebros and broettes? We're doing math on the internet, so don't adjust your TV set. Let's get linear. Hey, welcome. Today we're going to be taking a look at section 1.5, talking about solution sets of linear systems, and we're going to be focusing on the homogeneous matrix equation for this. So we have a system of linear equations is said to be homogeneous if it can be written in the form Ax equals 0, where A is an m by n matrix, and 0 is the zero vector in vector space Rm. So just to be extra clear about what we mean here, because clarity is important. I mean Ax equals 0, where here 0 refers to the zero vector. A is a matrix, x is a vector, equals 0, the zero vector. So not the number 0, but the zero vector. Such a system, Ax equals 0, always has at least one solution, namely when x is equal to the zero vector. And this isn't necessarily the same vector. This is the zero vector in Rn. And we'll sort of notice that it depends on, what we're looking at in terms of solving really depends on how many columns we have for the matrix. But so we're saying, okay, so there is always some solution, right? If x is the zero vector, then if I just have a vector of zeros, a times the zero vector will give me the zero vector out, meaning the zero vector of Rm. So that's always going to be a solution. However, this isn't really an exciting solution. In this case, we call the zero solution the trivial solution. You say, well, we're always going to have that. The question is that the only possibility, or are there others? So the zero solution is called the trivial solution. For a given equation, Ax equals 0, the important question is whether or not we can find a non-trivial solution. That is, a non-zero vector x that satisfies Ax equals the zero vector. So really we want to know, okay, I can solve this. It's always going to be consistent. I want to know whether or not there is a non-trivial solution, because that's more interesting. We're always going to have the trivial solution. You can always find that solution. But we want to know, is there some other solution? We have a nice theorem. Theorem says the homogeneous equation Ax equals 0 has a non-trivial solution if and only if the equation has at least one free variable. So if we're looking for non-trivial solutions, that means we're really hoping that we have a free variable to the system. And I'd like to start with an example. Determine if the following system has a non-trivial solution. Now I want to build this into a matrix equation. So I get to build my coefficient matrix. So here it looks like I can just take coefficients in order. That's 1, -2, 3 for my top row. Second equation, -2, -3, -4. And then the third row from this third equation should have coefficients 2, -4, and 9. And since it's a homogeneous equation, notice it's equal to 0 for all of these pieces. I'm going to augment this with the zero vector. And now I'd like to go ahead and solve. So we want to go through our row reduction, but I want to just start by saying the trivial solution is a solution. If x1 is 0, if x2 is 0, and x3 is 0, then all three of these left-hand sides of our equations are going to give me 0, and 0 equals 0, so it's going to give me a true statement. So right away, there is a solution, it is consistent, but I want to know, is there anything else that will work? Now let's row reduce, right? So here I can use this 1 in the upper left corner to try to get zeros underneath it, right? That's my leading entry. I want it to be the only non-zero entry in its column. So let's get these zeros underneath it. We can think about what operations we're going to need to do that. So here in row 2, I'm going to want -2 plus 2. So that should be replacing row 2 with row 2 plus 2 times row 1. And here to get rid of this 2 in row 3, I would want 2 minus 2. So I want to replace row 3 with row 3 minus 2 times row 1. And I can start just by rewriting row 1. Get that out of the way. And then going through the operation replacing row 2, I get -2 plus 2 times 1 gives me that 0 that I wanted. -3 plus 2 times -2, so that's -3 plus -4 gives me -7. And then -4 plus 2 times 3, that's -4 plus 6 gives me 2. And then here in the augmented cell, I'm just doing operations on zeros. So I get 0 plus 2 times 0 gives me 0. Something nice about these homogeneous equations is the augmented entries aren't actually going to change. And technically, you could just reduce the coefficient matrix and then bring the zeros back into play later. Don't forget it's an actual augmented system. But while I'm doing all these linear operations, the zeros aren't going to change, right? None of those elementary row operations are going to change when those operations are performed, only on zeros. So I like to keep it as part of the work. I think you should too, but you're not going to really notice anything fancy happening over here as it would with a non-homogeneous example. Well, let's continue. So now replacing row 3 with row 3 minus 2 times row 1. 2 minus 2 times 1 gives me that 0 that I wanted. Negative 4 minus 2 times negative 2, so that's negative 4 plus 4 gives me 0. And 9 minus 2 times 3, that's 9 minus 6 gives me 3. And then as promised, 0 minus 2 times 0 preserves my 0 there. And this looks like it's going to simplify pretty soon for us. If I notice here in row 3, I can actually scale this. So I could do a 1/3 row 3, just scaling it down. So I'll rewrite the rest of the rows. So there's row 1, row 2, and then here row 3. If I divide everything by 3, I'm going to get 0, 0, 1 augmented with 0. And now I'm noticing here this leading entry in row 1 looks great. If I look at it sort of column-wise, I'm really turning my attention to row 3 next. And what's nice about this, or the reason why I'm doing that, is because it's all zeros except for this leading entry, which is a 1. And this is going to allow me to very safely and very surgically get zeros directly above it. So that's actually going to be a really move to work on next. Perhaps it doesn't follow the perfect row reduction etiquette, but I think it's the most advantageous move to make next. Because what I can do is I can get rid of the 3 in row 1 and get rid of the 2 in row 2. And I can do that with the following row replacements. I can replace row 1 with row 1 minus 3 times row 3. And similarly, in row 2, I could do row 2 minus 2 times row 3. And I can just rewrite row 3 and just get that out of the way if I want. And you're going to notice this is going to almost too perfectly just remove those entries. So here I get 1 minus 3 times 0 keeps my 1. Negative 2 minus 3 times 0 keeps my negative 2. But 3 minus 3 times 1 gives me that 0 that I wanted. And then, of course, 0 minus 3 times 0 keeps my 0 in the augmented entry as well. And similarly, working in row 2, replacing with row 2 minus 2 times row 3, I get 0 minus 2 times 0 keeps my 0 there. Negative 7 minus 2 times 0 keeps my negative 7 there. But 2 minus 2 times 1 gives me that 0 that I wanted. And 0 minus 2 times 0 gives me the 0 that I wanted as well. So very safely and surgically, it just got rid of those 2 entries that I was trying to get rid of. So a very nice move to make. And from here, I can scale row 2. I can do negative 1/7 row 2. So here, rewriting row 1, I have 1, negative 2, 0, augmented with 0. Dividing everything in row 2 by a negative 7 gives me 0, 1, 0, augmented with 0. Row 3, I'm going to get 0, 0, 1, augmented with 0. Now the only thing left to do is really work with this, pivot entry here in row 2 in that second position. I want to get rid of that negative 2 above it, and I can very safely and surgically do this as well. Here I can work in row 1, replacing row 1 with row 1 plus twice row 2. So I get 1 plus 2 times 0 keeps my 1. Negative 2 plus 2 times 1 gives me negative 2 plus 2 gives me that 0 I wanted. 0 plus 2 times 0 gives me 0. And then again in the augmented entry gives me that 0 back. I can rewrite the rest. But I want you to notice what this is saying. So this actually tells me the answer, tells me all I need to know about the solution. And this is saying very specifically, the first row is saying x1 plus 0x2 plus 0x3 equals 0. Second row is saying 0x1 plus x2 plus 0x3 equals 0. And the third row is saying 0x1 plus 0x2 plus 1x3 equals 0. We typically wouldn't write it this way. This is a lot of excess stuff that I don't need to write. In fact, I think it's much worse to write it this way. What this is really saying is x1 equals 0, x2 equals 0, and x3 equals 0. Or if I want to write this as a vector, I could say, well, x is the vector with entries x sub 1, x sub 2, and x sub 3 in it, in which case all of these entries are 0, so it's the 0 vector. So what was the question we were asked, right? We wanted to know, is there some non-trivial solution? Determine if the following system has a non-trivial solution. We would say no. There is no non-trivial solution. And I like to just make things extra clear. I would write only the trivial solution exists. We saw our solution is this 0 vector, and we didn't get any free variables. That's all we got. So only the trivial solution. Let's take a look at a theorem. Suppose the equation ax equals b is consistent for some given b, and let p be a solution. Then the solution set of ax equals b is the set of all vectors of the form w equals p plus v sub h, where v sub h is any solution to the homogeneous equation ax equals 0. Well, okay, so let's think about this then. So what we're saying is, if I have a solution to the homogeneous equation, that can really be in there for free. So that shouldn't really make any difference here, right? So here we'd say, let P be a solution to AX equals B. We can actually show this with some proof idea. So we'll say P is a solution to AX equals B. And V sub H is a homogeneous solution which means that this is a solution to AX equals 0. And if I want to be extra clear about what this means, for P to be a solution to AX equals B, this means if I plug P in, A times P is equal to B. And for V sub H to be a solution to AX equals 0, that means A times V sub H is equal to 0. That would be the 0 vector there. Now I want to show that W, where W is P plus V sub H, is a solution as well. So W equals P plus V sub H. If I take a look at, we'll say, notice, A times W is the same as A times, I can replace W with P plus V sub H. And I can distribute through, so I'll say, okay, well, this is A P plus A times V sub H. And this is equal to, well, A times P, I know this is B, plus A times V sub H, I know that's going to give me 0. Think of that as the 0 vector. And then B plus the 0 vector is just going to give me B back out. So this is also a solution. So we'll say, so W, that's a W I'm trying to write there. So W is also a solution to AX equals B. So not so bad to show this or sort of get an idea as to what's happening there. We're going to focus on, in this section, writing a solution set of a consistent system in parametric form. And I'm going to talk a lot about these steps, but let's go ahead and sort of discuss them colloquially first. I want to start by row reducing the augmented matrix to reduced echelon form. Then I want to express each basic variable in terms of any free variables appearing in an equation. Remember, the basic variables are where we have our pivot columns. So if we got a pivot column there, it's a basic variable. If it's not a pivot column, it's a free variable. I want to express any basic variable in terms of any free variables appearing in an equation. Then I want to write a typical solution x as a vector whose entries depend on the free variables, if there are any. And then I want to decompose that vector x into a linear combination of vectors with numeric entries using the free variables as parameters. And it's not as bad as it sounds. I think you're really going to like this once we get going with it. And I'm going to talk all the way through the entire process. So now I want to take a look at this example. I want to find the solution set of the homogeneous system, and I want to build that solution in a parametric vector form. And let's start just by building our matrix equation, right? We need that first. So my coefficient matrix for this first row should be 1, 2, negative 3. I'm going to augment this, so I'll leave some room for that later. Second row should be 2, 1, negative 3. And then this third row, I got to be careful because x3 is missing, so negative 1, 1, 0. And all of these are equal to 0, so augmenting with the 0 vector. Now I want to start row reducing, so it isn't until I start building my solution that I can think about the parametric vector form. So let's start with some row operations. I can use this 1 in the upper left corner to get zeros underneath it. So there I'd want to replace row 2 with row 2 minus 2 times row 1. And I can replace row 3 with row 3 plus row 1. And let me rewrite row 1 to start. So that's 1, 2, negative 3, and then augmented with 0. And then I can go ahead and work in row 2. So I can do 2 minus 2 times 1 gives me 0. 1 minus 2 times 2, that's 1 minus 4, gives me negative 3. And negative 3 minus 2 times negative 3, or that's negative 3 plus 6, gives me 3. And then 0 minus 2 times 0 gives me 0 in the augmented cell. And then replacing row 3 with row 3 plus row 1, I get negative 1 plus 1 gives me 0. 1 plus 2 gives me 3. 0 plus negative 3 gives me negative 3. And 0 plus 0 gives me 0. So off to a good start so far. Now, I could go and scale. I'm going to want to do that at some point, but you could also reduce right away. So I could go and reduce in row 3, for example. Replace row 3 with row 3 plus row 2. I think that feels like a very human thing to want to do next. So I'll rewrite rows 1 and 2. Reducing row 3, I'm going to get 0 plus 0 is 0, 3 plus negative 3 is 0, negative 3 plus 3 is 0, and 0 plus 0 is 0 again. So I get a row of all zeros there at the bottom. I'm not quite done row reducing, but now I would turn my attention to row 2 and want to scale that. Let's say, well, let's scale row 2 by a negative 1/3. I can rewrite row 1. Dividing everything in row 2 by a negative 3, I get 0, 1, negative 1, augmented with 0. And row 3 is that row of all zeros at the bottom. Now everything's looking really good. I do have a leading entry in row 1 and a leading entry in row 2, no leading entry in row 3. But if I'm looking column-wise, the first column looks good, second column needs some work. I got to get rid of that 2. I got to replace it with a 0. So I can work in row 1, replacing row 1 with row 1 minus 2 times row 2. And we'll see how that's going to look. So I get 1 minus 2 times 0 keeps my 1. 2 minus 2 times 1 gives me that 0 that I wanted. Negative 3 minus 2 times negative 1, that's negative 3 plus 2 is going to give me negative 1. And then augmented with 0 minus 2 times 0 keeps my 0. And I can rewrite now row 2 and row 3. So just rewriting. Everything looks really great here. This is as far as I can row reduce. Now I'm ready to start thinking about writing this in a parametric vector form. So let's actually start just by writing out what these equations are saying. So this first row, as an equation, is saying x sub 1 minus x sub 3 equals 0. The second row, as an equation, is saying x sub 2 minus x sub 3 equals 0. And the third row is just saying, 0 equals 0, which that's not really of any interest to us. I also want to be thinking about my basic variables and my free variables. Let me put a B for basic and an F for free. If it's a pivot column, so here I have a pivot entry in this first column, that's a basic variable in this column. Here in the second row, I have that pivot entry, so the second column then is a pivot column, so I got a basic variable there. But this third row and that third column has no pivot entry, so that's where my free variable is. So really, what's happening is x sub 3 is the free variable, FV for free variable. And I want to solve my basic variables, x sub 1 and x sub 2, in terms of the free variable, which very natural to want to do that, just solve for x1 and x2. So x1 equals x sub 3. x2 equals x sub 3, and we can make a special note here that x sub 3 is free, our free variable. But now what I want to do is I want to build this into a parametric vector form. So we start off with this generic idea that our vector x is a vector with 3 entries in it, and those entries are x sub 1, x sub 2, and x sub 3 in general. But now in this vector description, this generic vector description, I want to substitute any basic variables for the free variables. So we said x sub 1 is x sub 3, so I'll substitute that. And x sub 2 is x sub 3, so I'll substitute that. And x sub 3 is itself, so I'm just going to keep that as x sub 3. But what's nice about this description is now I can bring the free variable x sub 3 out as a scalar weight. So I'll say if I just bring x sub 3 out, I get x sub 3 times the vector with numerical entries. What does this leave behind? It leaves behind coefficients 1, 1, 1. And this would be the parametric vector form of our answer. So we would say x is equal to free variable x sub 3 times the vector 1, 1, 1. And this is going to be a very useful process and approach for when we talk about things like building a basis for the null space, all sorts of cool stuff. But for now, we're just getting comfortable for the first time with parametric vector form. And if this feels a little bit strange, I think, the first time we do anything new in mathematics, it can feel that way. But trust me when I say we're going to get a lot of practice with the parametric vector form. In fact, we're going to see another example right now. So let's go ahead and take a look at the following. Describe all solutions of Ax equals 0 in parametric vector form, as promised, where A is row equivalent to the given matrix. So here I have this matrix A, and I want to think of the system Ax equals 0. So really what I'm going to be doing, and I could rewrite this and do it, is I want to augment this with the 0 vector. So I'll say, okay, so my system should be, I have 1, -3, -8, 5, and then I want to augment that with 0, and I have a second row, should be 0, 1, 2, -4, and I want to augment that with 0 as well. Now there's not a lot of row reduction to do. I have my pivot entry here in column 1, the column looks good. Another pivot entry in column 2, I got to get rid of that -3. So that seems to be perhaps the only step of row reduction I need to do. Let's do it. So I can replace row 1 with row 1 plus 3 times row 2. That's going to give me 1 plus 3 times 0 gives me 1. -3 plus 3 times 1 gives me that 0 that I had wanted. -8 plus 3 times 2, so that's going to give me -8 plus 6 gives me -2. And then 5 plus 3 times -4. So okay, so that's 5 plus -12 gives me -7. And then augmented with 0 plus 3 times 0 gives me 0. And I can rewrite row 2. So that was 0, 1, 2, -4 augmented with 0. Now this is fully reduced. That's all I had to do. Now I got everything is fully reduced. And if I'm noticing what's happening with my basic variables and my free variables, I have a pivot column in column 1. That's a basic variable for x1. I have a pivot column in column 2. That's a basic variable. But x sub 3 and x sub 4, which would be in columns 3 and 4, are going to be free variables. Those are not pivot columns. I have a free variable there. And I can make a note to myself. I think it's always good to make this note that x sub 3 and x sub 4 are the free variables, FV for free variables. But from here, we proceed just writing out what these equations are saying. So this first row is saying x1, skip over it, minus 2x3 minus 7x4 equals 0. And the second row is saying x2 plus 2x3 minus 4x4 equals 0. But my goal is to solve for the basic variables in terms of the free variables. So I want to solve for x1 and x2. So if I solve these, this first equation would be x sub 1 equals, I have to add these over. So x1 equals 2x3 plus 7x4. And then here, moving these to the other side, I get x2 equals negative 2x3 plus 4x4. Now I want to think about how my solution would look as a generic vector. All right, so here I can just go ahead and think about how many columns I have. I have 1, 2, 3, 4 columns. So my vector should have 4 pieces in it. So we'll start with the generic description. X would be the vector with entries x sub 1, x sub 2, x sub 3, and x sub 4. But now I want to start making substitutions in terms of the free variables. So here it's a x sub 1, that's 2x sub 3 plus 7x sub 4. So I'll swap that out. And x sub 2 is negative 2x sub 3 plus 4x sub 4. And now for these other 2 entries, they're really just the free variables, so they should stay as themselves. There is a nice trick that you can do though, so I'm going to show you that in a second. But we'll say here we have x sub 3 is equal to x sub 3, and lastly x sub 4 is equal to x sub 4. But if I want to try to see the parametric vector form even a little bit better, I can try to write even the free variables in terms of all of the free variables of the system. So I could say x sub 3 plus, and then I'm going to have to fix this later, but let me introduce x sub 4 there as well. And x sub 4 is equal to x sub 4, right? No identity crisis, but let me introduce x sub 3 in there as well. And let me build some coefficients in here. X sub 3 is x sub 3. And what we mean when we say that is x sub 3 is 1 x sub 3 and no x sub 4. And similarly, x sub 4 is equal to x sub 4, so it should be a 1 x sub 4 and a 0 x sub 3. But you're going to see why in the next few steps, why this might not be such a bad idea. Do you have to write it this way? No, I think you can still be successful finding the parametric vector form of the solution without building these sort of excess terms, but doing it really gets you there very nicely and very quickly. Because what I want to do next is I want to actually split this up into one vector in terms of x sub 3 only, and another vector in terms of x sub 4 only, and add those two together. So all my x sub 3 terms are going to be in this first vector, 2x sub 3 minus 2x sub 3, 1x sub 3, 0x sub 3. And then over here, all of my x sub 4 terms. So 7x sub 4, 4x sub 4, 0x sub 4, 1x sub 4. And now what I can do is I can bring the free variables out as weights. So here if I bring x sub 3 out, I'm left with a numerical vector, just numerical entries. It's the coefficients 2, negative 2, 1, 0. I'm going to add to this. Now I'm going to bring x sub 4 out as a scalar weight, and I'm left with the vector with numerical entries 7, 4, 0, 1. And then this is equal to, we call it x. And this is my parametric vector form of my solution. So this is how my final answer is going to look. And if you want to find a specific solution, you could then pick values for x sub 3 and x sub 4. So if you wanted to show non-trivial solutions, you could show specific ones. This is how the solution set looks. We have that parametric vector form of our solution. Let's see another example. We're here to get comfortable with the process. So I want to describe all the solutions to Ax equals 0 in parametric vector form, where here I have this matrix A. So first thing I want to do is I want to rewrite this and augment with the 0 vector. So augmenting with 0. Now I want to start row reducing. I'm going to scale both of these rows. I'm going to do a negative 1 times row 1. So I'm going to flip all the signs there. So positive 1, positive 4, 0 is signless, positive 4 augmented with 0. Row 2, I'm going to cut everything in half. I'll do a 1/2 row 2. That's going to give me 1, negative 4, 0, 4 augmented with 0. They almost look identical, but now I can go ahead and row reduce a bit. I'm going to replace row 2 with row 2 minus row 1. See what that looks like. So I'll rewrite row 1 to start. Then here in row 2, I get 1 minus 1 gives me 0. Negative 4 minus 4 gives me negative 8. 0 minus 0 gives me 0. 4 minus 4 gives me 0. And in the augmented entry, 0 minus 0 gives me 0. Now I'd want to scale row 2. I can do a negative 1/8 row 2. So here row 1, I'm going to replace it, 1, 4, 0, 4, and then augmented with 0. Row 2 is going to be 0, 1, 0, 0, augmented with 0. Now I want to try to get rid of that 4 in the second entry of row 1. I want to get a 0 there. So I can work with my row replacement. So I can replace row 1 with row 1 minus 4 times row 2. Should be the winning operation there. 1 minus 4 times 0 keeps my 1. 4 minus 4 times 1 gives me 0. 0 minus 4 times 0 gives me 0. 4 minus 4 times 0 keeps my 4. And then augmented with 0 minus 4 times 0 gives me 0. And then I can go ahead and rewrite row 2. You know what we like to do? We like to go ahead and figure out what our basic and free variables are. Here I have pivot column in column 1, pivot column in column 2. These are my basic variables. Columns 3 and 4 are not pivot columns. Those are my free variables. Free variables. So I like to make a note. So here I'll make the note over here. X sub 3, X sub 4 are the free variables to the system. Let's write out what these equations are saying. So this first row is saying x sub 1 plus 4x sub 4 equals 0. And the second row is saying x sub 2 equals 0. And I want to write these, I want to solve for these in terms of the free variables. So I can go ahead and actually start doing that. In fact, there's not really much I can say here. I can say x sub 1 is equal to a negative 4x sub 4, and x sub 2 is equal to 0. And x3 and x4 are my free variables. But to build that parametric vector form of the solution, what I want to do is I want to try to get everything in terms of all of my free variables. So I'll say, okay, x is this vector with entries x sub 1, x sub 2, x sub 3, and x sub 4. And x sub 1 is a negative 4x sub 4, but I don't want to maybe not mention x3, so I'm going to say, okay, well, it's 0x3, and then plus negative 4x4. And x2 is just 0, but even better, and this is going to maybe seem a little strange, but trust me when I say it's better, I can think of this as 0x3 plus 0x4, which is still 0. Might seem kind of weird to write it, but I can start to see those vectors forming. And x3 is itself, and x4 is x4, right? x4 is itself as well. But remember, we said it's a good idea to build coefficients and to write in the other free variable. So x3 is 1x3 plus 0x4, and x4 is 1x4 plus 0x3. Because the advantage now is that I can split this up into the two vectors, one vector relying on only x sub 3, and then plus another vector relying only on x sub 4. And it's really going to make seeing the vector a lot easier. So x sub 3, that's 0x sub 3, 0x sub 3, 1x sub 3, 0x sub 3. Not a lot going on. My vector for x sub 4, that's negative 4x sub 4, 0x sub 4, 0x sub 4, 1x sub 4. And now what I can do is I can bring the scalar weights out. So bring the free variable out as a scalar weight. So x sub 3 times the numerical vector with entries, there they are. I'm looking right at them. I don't have to guess at it. 0, 0, 1, 0, plus bring x sub 4 out as a free weight. I'm left with the vector with numerical entries, negative 4, 0, 0, 1. And this is my solution for x. I have my parametric, the vector form, giving me my description for my solution. And it looks great. We love this. We love this. There it is. Take a look at one more example. You're thinking more examples. I'm thinking more examples. So we're both thinking the same thing. So let's go ahead and see what we can do. So here, like I was saying before, it's a good idea to augment with the 0 vector. But since the operations on zeros don't change, I can just reduce the coefficient matrix, and that certainly suffices. Now, I'm noticing I have a row of all zeros at the bottom. Here I have all these zeros and then a 1 at the very end. I can use that to get zeros above it. So let me actually just start here with an operation in row 2 and replace row 2 with row 2 plus 6 times row 3. So I'm going to rewrite row 1. I'm going to go ahead and augment as well, since I think it's the right thing to do. But replacing in row 2, 0 plus 6 times 0 gives me 0, and then again, and then again. 1 plus 6 times 0 keeps my 1. 4 plus 6 times 0 keeps my 4. Negative 6 plus 6 times 1 gives me that 0 that I wanted. And I'm augmenting this, and the operation on zeros will stay 0. Really nice about the homogeneous systems. I can rewrite rows 3 and 4. And I'm augmenting. Okay. So it looks really good. I like the pivot column in column 1. Pivot column in column 4 has got to get some special treatment. Pivot column in column 6 looks good. So really all that's left for me to do, focusing on this leading entry in row 2, looking beneath it and above it, it should all be zeros. Oh, I got to get rid of that -6 then. So then I want to do some row replacement, replacing row 1 with row 1 plus 6 times row 2. So I get 1 plus 6 times 0 gives me 1. -2 plus 6 times 0 keeps -2. 3 plus 6 times 0 keeps my 3. -6 plus 6 times 1 gives me that 0 that I wanted. 5 plus 6 times 4. So I say, okay, well, that's 5 plus 24 gives me 29. And then 0 plus 6 times 0 gives me 0. And then augmented with, again, 0 plus 6 times 0 gives me 0. And I just want to rewrite the rest of the rows. So row 2 was 0, 0, 0, 1, 4, 0, augmented with 0. Row 3 was 0, 0, 0, 0, 0, 1, augmented with 0. And row 4 is my row of all zeros. And then augmented with 0. And let me check my pivots and their columns. Looks good. Pivot, column looks good. Pivot, column looks good. All right, let's talk about our free variables. If it is a pivot column, the variable that lives there is the basic variable. In column 1 is where x of 1 lives. It is a basic variable. Column 2 is not a pivot column. This is where my free variable is. Column 3 is not a pivot column. Got another free variable there. Column 4, I got a basic variable. This is a pivot column. I can sort of circle the pivot positions. But then here, if I go to column 5, not a pivot column, free variable. And then here, column 6, that is a pivot column, right? There's my pivot. And this last row doesn't really give me any information, but it's there. So what are my free variables? x2, x3, and x5. So x2, x3, and x5 are the free variables to the system. And I want to keep that in mind when I go to write my solution. So okay, so what are these rows trying to tell me? Well, the first row says x of 1 minus 2x of 2 plus 3x of 3 plus 29x of 5 is equal to 0. Second row, so we got 0x1, 0x2, 0x3 says 1x4 plus 4x of 5 equals 0. And this third row says 0x1, 0x2, 0x3, 0x4, 0x5, x6 equals 0. And the last row just says 0 equals 0. It's not telling me anything useful necessarily. But now I want to solve these equations in terms of the free variables x of 2, x of 3, and x of 5. And it's always a bit tricky to do this if they're not mentioned in any given equation. But let's see if we can do this. So for this very first one, this very first equation here, I would solve for x of 1 is my basic variable. And x of 1 equals positive 2x of 2 minus 3x of 3 minus 29x of 5. Solving in the second equation, we would say x of 4 equals negative 4x of 5. And then here, this last basic variable, x of 6, is just equal to 0. But you know what we're going to do. We're going to try to write these out a little bit better. These are going to be big vectors. So x has x of 1, x of 2, x of 3, x of 4, x of 5, and x of 6 to consider. And x of 1 actually has all of my free variables. That's 2x of 2 minus 3x of 3 minus 29x of 5. X of 4, so let me actually do the free variables then. So x of 2 is x of 2. X of 3 is x of 3. And then x of 4 is a negative 4x of 5. X of 5 is a free variable. X of 5 is equal to itself. And x of 6 is just 0. So I start to sort of build this, get a sense for how it looks. But I think it's really helpful to fill in those missing pieces. So let me go back through. X of 1 is already taken care of. That's always nice when that happens, I guess. But the rest shouldn't be so bad. x sub 2 is 1x sub 2 plus 0x sub 3 plus 0x sub 5. And x sub 3 is 1x sub 3, but then also a 0x sub 2 and a 0x sub 5. And x sub 4 is a negative 4x sub 5, but that also means a 0x2, a 0x3, and then that minus 4x5. X sub 5 is 1x sub 5, but also 0x sub 3 and 0x sub 2. And since x sub 6 is just 0, we can safely write this as 0x sub 2 plus 0x sub 3 plus 0x sub 5. Now I can really start to see this taking form. And I'm almost running out of space, so let me sort of skip the next step of the vector decomposition and write the result. But you can see the vectors if you look at it sort of in a vertical fashion. So x is equal to, I have a vector that relies on x sub 2. What should the numerical entries be? Well, here they are, 2, 1, 0, 0, 0, 0. Plus, now I have a vector that x sub 3 is multiplying to as a free weight. What should the numerical entries be? Negative 3, 0, 1, 0, 0, 0. And then plus, now I have x sub 5 times a numerical vector. I wonder what those entries should be. Well, of course, negative 29, 0, 0. So negative 29, 0, 0. What are the rest? I gotta get my face out of the way. Negative 4, 1, 0. Oh, that one didn't do. And this is our parametric vector description of the solution. So here we got it. This is our answer. Let's talk about what this means sort of geometrically, or why we sort of care about it so much. I want to describe and compare the solution sets of, here I have very similar equations, x sub 1 minus 2x sub 2 plus 3x sub 3 equals 0, and x sub 1 minus 2x sub 2 plus 3x sub 3 equals 4. And I'm not going to worry so much about writing the matrix that this would come from. It really wouldn't be too interesting. I can actually solve this for x sub 1 in each case. That would be my basic variable, right? It would be just one row that I'm really considering. And these are two separate equations. So solving this, I get x sub 1 equals 2x sub 2 minus 3x sub 3. Solving this other one, very similarly, x sub 1 is 2x sub 2 minus 3x sub 3, and then plus 4. And if I write these out as solutions, and here these should be solutions in terms of free variables, where here x sub 2 and x sub 3 are the free variables. This first equation here, I'd say, well, okay, so then x is equal to, and it should be x1, x2, and x3. X sub 1 is 2x sub 2 minus 3x sub 3. And x sub 2 is, 1x sub 2 plus 0x sub 3. And x3 is 1x sub 3 plus 0x sub 2 as the free variable. So this builds for me in parametric vector form. I get x sub 2 times the vector 2, 1, 0 plus x sub 3 times the vector negative 3, 0, 1. So what about the other? Let's do a different color for this. Very similar, but there is a difference here, right? So I'd say, well, x then should be a vector with entries x1, x2, and x3. x1 is 2x2 minus 3x3 plus 4. x2 is 1x2 plus 0x3. And x3 is 1x3 plus 0x2. And if I go ahead and split this up into vectors, I want you to think about this very carefully, because I'm not just going to be able to get away with two parts to my solution. There is actually a third part that I'm going to need. I'll go ahead and explain that. So here the part relying on x sub 2 is really the same as it was before, 2, 1, 0. The part relying on x sub 3, I can follow along here, negative 3, 0, 1. But since I have this 4, in this very first entry, I need to add on this sort of so-called intercept vector 4, 0, 0, so that x1 can still be 2x2 minus 3x3 plus 4. Right? I need that 4 there for that entry, so I need this third vector. And how can I think about these? Well, in general, my solutions, or the parts that are the same, I get this sort of x equals, here I get x sub 2 times some vector, call that vector p, plus x sub 3 times some vector q. And so what this is, or how this looks geometrically, this is going to be the plane through the origin dictated by vectors p and q. Think of this like a span is really the idea. However, what's different then about this one, because it looks very similar, this one is a little bit different. This one is going to be x equals x sub 2 times, I have that same vector that I called p, so I can write it that way again, and then x3 times that same vector that I called q, but then plus this intercept vector 4, 0, 0. Or you could give this vector a name as well, but here I'm going to say this is the plane also dictated by vectors p and q, but through this vector 4, 0, 0. But through the vector 4, 0, 0. And if I want to get some idea as to how this would sort of look maybe visually, I'm not going to try to do too painstaking of a job drawing this. That can be sort of my grid in 3 space. This first one, so I did that in sort of the purple. I have this plane dictated by these vectors. So how would that look? Well, here I have, vector p, vector q. I'm really thinking about the span of this. So I get some plane dictated by these. And then we end up getting all possible linear combinations in that span. So I get this plane here. But the plane is through the origin. What's different about the second solution in pink, it's really the same plane, except it's been shifted, right? It has this different intercept vector at 4, 0, 0. So I can think of it as being translated in the x1 direction, however that sort of looks. I'll just draw it up here for the sake of convenience. But it should really be the same otherwise. I have vectors p and q in the same regard, but it's been shifted up. And then I get all of those, scalings of those. I'll try not to draw, I can't really draw all of these without sort of interrupting the picture that I'm trying to use to describe. But I think we get sort of the idea. So it should be the same plane. So I got the one plane through the origin, and I have same plane but just shifted up. Right, shifted up through that vector 4, 0, 0. Let's take a look at one last example, and then, hey, we're going to get out of here. So I want to find a parametric equation of the line m through vectors p and q. And we get a little hint here. Notice that the vector q minus p is parallel to that line m. I think a fair question is how or why. Let me try to give you some visual sense here. I hope the picture turns out good. But let's say we have vectors p and q. I'm not going to try to draw these vectors in particular, but I'll just draw some generic vectors. Let's say this is vector p. I'll get a different color here for vector q. Give me that color. I'm considering the line through vectors p and q. But now, if I want to talk about q and then minus p, that means I really want to draw the vector minus p. So I'll go back to the purple for that. So if this is vector p, then minus p would just be in the opposite direction. Should be about the same length, kind of close. And to find q minus p, I want to add q and minus p together. So think about translating this as my vector minus p. And then I want the resultant. So the resultant then, let me do that in blue, would be from the origin here to the tip of that vector. So like this. And it would just be the vector that stops there, but I drew it a bit further. So that would be the vector q minus p. But then if I consider the line m, and the line m is through vectors p and q, that would be just running a line through vectors p and q. And maybe not super convincing with my picture, But this blue line is parallel to this red line, is what I'm trying to depict. That q minus p is in fact parallel to this line m, which goes through vectors p and q. Why does that matter? Why is it important to know that? Well, what we're going to do is we're going to use this vector q minus p to build a slope vector. And what we're going to do is going to be very similar to building the equation of a line, like you would have done back in a pre-calculus course. So first I can find q minus p. So q minus p, I want to subtract the vectors. So take vector 0, minus 3, and subtract away negative 3, 2. And this is going to build a new vector for me. So vector q minus p as a new vector. 0 minus negative 3 gives me 3. Negative 3 minus 2 gives me negative 5. So I get this new vector, and this is going to behave as my slope vector. But from there, all I'm going to need now is an intercept vector. My intercept vector, I can pick one of these two vectors, sort of thinking of them like points. Doesn't matter if I pick p, doesn't matter if I pick q. I'm going to pick p, you could pick q. I'm going to pick p, you could pick q. So here I'm going to use p as my sort of point vector, and I'm going to build this. If I want to call it something, I can call it, x. I'm going to build this. I'm going to actually write down the generic description of it first. I'm going to use q minus p as my slope vector. I need a parameter. I'm going to use parameter t. Seems safe. And then plus I need one of my sort of points in here. I'm going to use p for that. But you could use q. So then how is this going to look? Well, here I'm going to have this vector q minus p. I just found it. 3 minus 5 are the entries. Times I need a parameter, which is t, plus vector p. You could pick vector q. For vector p, that was negative 3, 2. And then I could leave it like this. This is meeting the objective. Or what's nice is you could actually write these out as the separate pieces. So I might use a curly brace notation for this and say, well, here I have 3t minus 3, sort of going along the upper entries, and then the second entries, negative 5t plus 2 would be good. You could call these separate entries x1 and x2 is fine, but this is the description of what that is. So a question asked, find a parametric equation of the line m through p and q. This is that parametric equation. Right, this is the description of that line. Hey, I hope you found this to be interesting. I hope you enjoyed this lecture. Let me know what you think about all this stuff in the comment section below. We're going to be working with these parametric vector descriptions a lot in the course. So, get comfortable with them because they're here to stay, definitely. No matter where you are and what you're doing, I want you to always keep learning, keep dreaming, and follow your heart. And you know what? We're going to be back doing more math soon. But, until then, I will see you next time. And make sure that you take care of it.